Hi everyone, it's Mr. Hamilton here for a video on exponential growth and decay. We're going to look at a situation like on the left of exponential decay and a situation on the right of exponential growth. So our goal is to analyze the characteristics of rapidly decaying and rapidly increasing functions. So we're first going to look at a decay situation. Example 1 is bounce height versus the number of bounces. So if we drop a ball, it's going to bounce up to a certain height, and then it's going to bounce to a lower height and a lower height and a lower height. And so, for example, if we drop that ball and there's the ground, we're going to see that it's not going to come up as high as it was originally, as I noted. And then it's going to bounce again, and it's not going to come up as high as it was that second time. And so that's going to happen. In this case, 7 bounces are going to occur, and we're going to measure the heights before and after those 7 bounces. And so we can note, is it going to be a linear relationship? Is it going to be some type of curved relationship? Let's see what it is by analyzing first the first and second differences and then graphing it as well. So the first thing we're going to do is look at the first and second differences. The first differences, we take the second y value and subtract the previous y value. So 4.56 minus 6. It's always the later minus the earlier y value. And we're going to do that again with the 3.47 minus 4.56. And what we're going to get in each of those cases, in the first case, we get negative 1.44. In the second case, we get negative 1.09. I'm not going to draw out the 2.63 minus 3.47, but that's what we're going to do. And we get negative 0.84. Doing the same with the next one, we get negative 0.63. Then we get negative 0.48, negative 3.36, and negative 0.28. And so now we take the second differences. So we take the later value minus the earlier first differences. So negative 1.09, and we're going to subtract from that negative 1.44. And what that's going to give us is it's going to give us a value of 0.35. We're going to do the same thing with the negative 1.09 and the negative 0.84, and we get 0.25. Negative 0.63 minus negative 0.84, we get 0.21. Do the same thing over and over, we get 0.15 for the next one. We get 0.12 for the next one and 0.08 for the last one. Now, one thing to note here is that if the first differences are the same, it's linear. So it's not linear here. If the second differences are the same, it's quadratic. So we can say it's not quadratic. So it's neither one of those. So what is it? Well, one of the ways for us to tell if it's actually exponential is to look at the factor that all the y values are multiplied by. If they're multiplied all by the same factor, and in fact here they are, they're all multiplied by 0.76, that is the defining characteristic of whether or not it's exponential growth or decay. And we can see that as well with the first and second differences. The first differences, all these values are multiplied by 0.76 all the way through. Now they start getting a little bit of rounding error there, and then when you look at second differences, if you tried to multiply all those, you would get 0.76 as well with quite a variation. That's all due to rounding error. The idea is that multiple of 0.76 will be the same for all the differences. So it's exponential because there's a common multiple between the differences. So let's look at the graph of what happens here. On the y-axis, we're graphing the bounce height, and on the x-axis, we're graphing the number of bounces. Now, it looks kind of like the path at which the ball took, but what these points are how high the ball bounces to each time. And so if we join those dots together, what we end up getting is you end up getting this nice smooth curve. It's not a linear relation. What it is it's something that gets less and less steep. Less and less steep. Another way to describe that would be to say that it opens up. But continues decreasing. Continues decreasing. So it continues decreasing while it opens up. Now let's describe the domain and range. The domain is all the possible x values, all the possible independent values. So what that means is, in this case, we're dropping the ball from some height of 6 meters, and it hasn't had any bounces yet. And so we're starting at 0, and it's going to continue to bounce in theory forever. Even after 100 bounces, it's still going to be barely bouncing, probably not noticeable to us, but it will, in theory, still be bouncing according to this model. So what we would say is that x is a set of all real numbers such that x is greater than or equal to 0. So we said it's not bouncing from where it's dropped from. So that counts as the first drop. That's 0. The range is the possible y values. And the range here, we could say, is y is a set of all real numbers such that, well, y is actually going to be less than 6. It's starting at 6, and then it's going down and not quite becoming 0, right? It's always, as we said, going to have a little bounce to it still. So that's what we call in math a limit. So that means that y will always be greater than 0, and it will be less than or equal to 6 because it started at a height of 6. So it's greater than 0, less than or equal to 6. It's between 0 and 6. It's not 0, but it does get to 6. So that's how that is written, and that's what that means. Now, for example 2, the growth of a population. We could have the population of any animal. In this case, some animal it's going to be. It could be a tiger, it could be a lion, it could be an insect, it could be anything you could imagine. But we're going to talk about the number of years past a certain point and then the population of those years. Now, you notice here that the number of years doesn't go up one at a time like it did before. In fact, here it's going up every 2 years. The key to notice that it's exponential and to see the first and second differences is that there needs to be a consistent increase in the x value. So a consistent x value increase. In this case, it's going up by 2s, so we can totally use the first and second differences to analyze that. So let's do that. The first value we take is 6,000. We subtract 4,000 from it, so that gives us 2,000. 9,000 minus 6,000 gives us 3,000. 13,500 minus 9,000 gives us 4,500. And so we continue doing that later value minus the previous value, and we get all those first differences, and then we do that again for the second differences. And we can see that there's no common value that they become. There's no common first differences or common second difference. So at which point we start looking at the multiples, and we see that they're all multiples 1.5 of the previous number. Now, if the y values increase by multiples of 1.5, so do the first and second differences, and we can see that here. So we know it's not linear, it's not quadratic, we know it is actually exponential. And so as soon as we see those common multiple of all the values, that's the defining feature that something is exponential. So let's look at the graph now. The population we're going to graph on the y-axis, that's the dependent variable, and the time in number of years, or the time since we started measuring that population in number of years, is going to be on the y-axis. That's the independent variable. So the first thing we're going to graph is the point 0, 4,000, because it starts at a population of 4,000. Pause the video and add the rest of the points now. All right, so here are my points been added to the video. And so we're going to also give it a title. So this is the animal population versus time in number of years. And so what we're going to get is a nice smooth curve that gets steeper and steeper all the way along, as you can see from the trend of the data here. It's getting steeper and steeper. It's still opening up, just as it was before, and so we're going to describe it with those terms. Steeper and steeper, but it's never going to completely get vertical, though it's going to get very close. The other way we could describe this is that it keeps going up, it curves upwards, keeps going up and curves upwards. Again, we could say that that means it opens up, just like we did with the previous situation. All right, so now we go ahead and we list the domain and range. The domain is the possible x values here. And so we're starting at some time 0. And so we say x is greater than or equal to 0. It's going to keep going on past year 12, we're assuming. And the range is the possible y values. It's going to start at 4,000 and go up from there, keep going. So we're going to say that y is greater than or equal to 4,000. Now, one thing to keep in mind here, while this is a situation, is that oftentimes with populations of animals, bacteria, anything like that, there eventually is a point at which it branches off that exponential growth, and it reaches what's called the carrying capacity. That carrying capacity is generally where the population is pretty steady, though sometimes the population may go up and down a bit from there. But what that is due to is it's due to a number of factors. It's due to things like the habitat space. Might not have enough space for other animals to live. Might have limited resources, might have limited water or food. That's a very defining feature of can an animal survive if it doesn't have enough food to eat or water to drink. And lastly, competition with other species. So we have looked at two situations. We've looked at, on the left, a situation where we had exponential decay, and the situation on the right, the second example, where we had exponential growth. Now, as we just review that, we notice that they both open up. The one curves downwards and gets less and less steep, whereas the other curves upwards and gets more and more steep. And in the first and second differences, we noticed that there was no consistency with numbers there. And so it was a constant multiple that we noticed that showed us if it was an exponential. And we were able to write the domain and range from those graphs. Hope that was helpful. If you like this video, please give it a thumbs up and consider subscribing. Thanks.